Hello everyone, I'm Toby, a Senior Applications Engineer from Skylark Lasers. Today I'm going to discuss the manufacturing technique of laser interference lithography and how our lasers can provide optimal results when using this application. At Skylark Lasers, we specialize in the development of high-power UV single-frequency diode-pumped solid-state lasers. Our patented laser architecture allows us to provide unrivaled laser performance to enable the development of the next generation of laser interference lithography setups. Interference lithography is most commonly used for semiconductor manufacturing. However, it can also be used to produce other nanostructures such as optical gratings. Interference lithography is much easier to set up than E-beam lithography. Laser interferometry is a common maskless technique, and it is much easier a setup than other forms of laser interference lithography. As you can see from the diagram, the laser beam is expanded before it reaches the mirror and photoresist coated sample. The pinhole is used for spatial filtering, and an interference pattern is created in the sample by the direct illumination beam and the reflected beam. This produces structured lines of well-defined spacings. In any form of interferometry, coherence length is vitally important. Our UV lasers have a narrow line width of less than 500 kHz. Therefore, the coherence length will be more than long enough for any setup. Typically, with laser interferometry, the exposure times can be anything from 20 seconds to 10 minutes. This emphasizes the need for wavelength and power stability over this time. Pointing stability is also paramount, as any angular misalignment will lose the interference pattern or will create blurring of the structured line pattern that's created. To ensure that there is a uniform exposure of the photoresist, the Gaussian beam is typically expanded to 5 times the size of the photoresist. The smallest feature size that can be reduced is called the critical dimension and is related to the period P. For Lloyd's interferometric setup, P is determined by lambda over 2 sine theta plus this error term. Error is a combination of properties of the photoresist, the laser line width, the wavelength stability, and divergence changes of the laser beam. Blurry structures can be obtained from lack of wavelength and pointing stability. In addition, if the laser has a poor coherence length, this can affect the interference pattern that is produced. In addition to these laser parameters, it's vitally important to have a high level of thermomechanical stability for the whole setup to allow for reproducible nanostructures. Also, people can experience poor modulation depth after etching because of the poor reflectivity of the mirror. Feature sizes of anywhere between 160 to 800 nanometers can theoretically be achieved using our 320 nanometer NX. There are a large range of photoresists available for wavelengths around 365 nanometers. This is because they were all developed using a mercury lamp transition. Therefore, the 349 NX is well suited for these. In addition, the high power of up to 250 milliwatts of our 349 and 320 NX systems allow for large surfaces to be exposed by beam expansion. Large surfaces can be exposed using other techniques such as Mach-Zehnder interferometry. As you can see from these graphs from a 320 NX system, we've achieved a power stability of around 1% over a 25-hour period. The power stability is imperative to ensure accurate illumination times. This wavelength stability will produce exceptional well-defined gratings on your substrate. In addition, the spatial mode properties of our lasers will allow for effective re-imaging of the beam to ensure a uniform illumination. We offer UV lasers in various form factors to meet different customer OEM needs. Reach out to us at sales@skylark.com to find out more.